there are other ways to show the result that we want. First place, delta alpha radial, as we saw before, is r omega f squared minus r omega I squared, because radial acceleration is r omega squared. So the initial, the final, you subtract the initial from the final, you get the change in the quantity, and that should be equal to this, and that's what we're trying to prove. So, put a question mark here, question mark here. Is this equal? Well, it is, if and only if this is equal. The 2 alpha delta theta should strike a chord if you know the equations of uniformly accelerated motion. Okay? Where does this occur in the equations of uniformly accelerated motion? What's the meaning of that? Well, don't know if we're going to really get to the meaning of it, but we have the equation omega f squared equals omega naught squared plus 2 alpha delta theta. That's where you see it. So the 2 alpha delta theta equals omega f squared minus omega naught squared. So plugging that into here, this equation is 2 alpha r delta theta. Well, the 2 alpha delta theta takes up everything here except the r, so that's going to equal r times omega f squared minus omega I squared. Now, I used omega naught squared because that's what I generally use. That could be omega I. The naught could be replaced with the I, or the I could be replaced with the naught. Doesn't really matter. Well, this is clearly true. So we're done. So that's one way of doing the argument using the equations. Okay, I don't prefer that as a way to do it because there's no real insight involved in it. It's just a manipulation of symbols. Unless you really understand what 2 alpha delta theta is, the change in omega squared. I left the square off there. I don't think there's a whole lot of insight to be gained by doing it this way, but this is certainly a way to do it, and there are plenty of cases in physics where you just find the equation and excuse me, match things up as we did here and get a really useful result, whether you completely understand it or not. Another way to approach this is the derivative of a radial with respect to t. Well, a radial being r omega squared is the derivative with respect to t of r omega squared. R is constant in this case, so that's r times the derivative with respect to t of omega squared. And that derivative, omega is itself a function of t, so this is the square of the omega function, so you have a chain rule here. This is going to be r times 2 omega d omega dt. And if you don't understand that, go back and review your first year calculus. Make sure that you do. Okay? It's something not everybody's going to understand if they haven't seen it in a while. It's the chain rule. Okay? You work it out. And, of course, if you have a question, get it to me. Okay, so what's this? This is 2r omega. D omega dt is just alpha. Okay? So we have this relationship, and this relationship looks a whole lot like this one, except that, of course, this is the derivative of this relationship. So that how would we use this relationship to get back to here? Now, the derivative of a radial with respect to t is the rate at which a radial changes with respect to t. So the change in a radial equals the derivative of a radial with respect to t times delta t. And that would equal this times delta t. So that's 2r omega alpha delta t. And that would be what? Well, we could multiply alpha by delta t to get omega squared here. Okay, because alpha times delta t is the change. Well, we wouldn't get omega squared. Alpha times delta t would be a delta omega. So that could be 2r omega delta omega. Or we could choose to multiply the omega times delta t, which would give us 2r times delta theta times alpha. Well, the 2r delta theta times alpha hits the nail on the head. So that the change in A radial is this. Now, this could also be useful in certain situations. So in summary, we see at least 3 ways to prove this relationship. One of them involves calculus and derivatives and differentials. One of them involves just recognizing something in the equations of motion without really understanding the meaning. There's more meaning in this than there is in this. And the original solution that you saw earlier, where we just start with delta A radial and kind of follow our nose with a deep understanding of what the different quantities actually mean. Each approach has its own insights and its own merits. There's nothing better or worse than any of them, except I do urge you to try to find deeper results. For example, this one or the first one, rather than just putting together a bunch of symbols. Not that it's undesirable to be able to put together the symbols, and not that that's not a very profound ability, but you want to complement it. And also, if you have the insight to do some of these others, you want to look at this as a nice, simple way of getting the result and try to understand what insights you can get from this sort of solution.